Look at a photograph and you immediately register objects, people, and depth. But computers process nothing of the sort. They only interpret a dense, chaotic grid of numerical pixel values. Early computer scientists tried to teach machines to interpret these grids by writing strict geometric rules. They instructed the computer to look for specific angles, rigid shapes, and mathematically perfect lines. The approach failed immediately in the physical world. A slight shift in the subject's position, a shadow cast across a room, or harsh lighting instantly broke those brittle, hard-coded instructions. Programming artificial vision line by line proved impossible. Engineers realized the machine needed an architecture capable of learning to see by mimicking the biological structure of the human visual cortex. The mathematical engine that makes this possible is the convolutional neural network, and it begins with a component called a kernel. A kernel is a small matrix of learnable mathematical weights. This illustration shows a 3x3 filter sliding incrementally across the input image pixels to create a convolved feature map. As the kernel moves, it performs localized dot product calculations on small clusters of pixels. By multiplying the underlying pixels against the kernel's weights, the network produces new numerical values. These resulting numbers act as a highly specialized detector, designed to activate when they encounter structural patterns like vertical or horizontal edges. The act of convolution takes a meaningless grid of raw pixels and transforms it into an organized topological map of structural features. Extracting feature maps for every single edge across an entire high-resolution image creates an overwhelming, computationally expensive bottleneck of data. This color-coded grid illustrates a 2x2 max pool filter extracting data to reduce spatial dimensions. Engineers introduced this compression step, known as max pooling, to solve the massive data bottleneck. The layer scans a given region of the grid and aggressively discards all data, keeping only the absolute highest numerical value, in this case, selecting the 6, 8, 3, and 4, while throwing the rest away. Extracting only the highest value grants the network a property called translational invariance. If an edge shifts slightly to the left or right in the original image, the pooled maximum value remains the same, allowing the network to still recognize the object. Pooling forces the machine to prioritize the existence of a visual feature over its exact pixel coordinates. As this data passes through multiple alternating layers of convolution and pooling, the network's receptive field expands dramatically. This deepening field allows the network to build a hierarchy of understanding. It combines simple edges into distinct textures and then merges those textures into recognizable, complex shapes. However, this immense learning capacity creates a serious vulnerability known as overfitting. A deep, complex network will often memorize the exact training data rather than learning general visual rules that apply to the real world. This diagram shows a neural network where half the hidden nodes are faded and inactive. Engineers use this technique, dropout, to counter overfitting. Randomly turning off connections forces the network to rely on multiple independent features. By stacking localized feature extraction, spatial data compression, and aggressive regularization, researchers constructed a reliable engine that achieves true visual hierarchy. Modern CNN architectures solve spatial problems that involve more than identifying the primary subject of a photograph. Engineers evolved the pipeline into fully convolutional networks. These strip away the standard classification layers at the end of the process and replace them with upsampling decoders. This architectural schematic shows the transformation of an input image through an encoder and decoder to output a red segmented mask. This process, called semantic segmentation, allows the network to classify the identity of every single individual pixel on the screen. This per-pixel classification provides the exact physical boundaries of every distinct object within a frame. Today, this pixel-level semantic segmentation operates in high-stakes environments. In medical imaging, the architecture actively parses intricate chest CT scans to identify and isolate microscopic lung nodules and tumors. The exact same underlying hierarchical math empowers autonomous vehicles to process continuous video streams. It instantly separates the boundaries of pedestrians, roads, and other vehicles to navigate chaotic physical environments safely. This hierarchical math provides the structural framework for machine spatial awareness in both medicine and robotics.